All right. All right, this is all out of 16. The other thing to think about these dienes, like you can have more than one. I have notes for this. I wonder how well I stayed with the notes. I've given this lecture a few times. All right. Still in 16. So we're going to look at how molecules absorb light and how we can predict or compare how they'll absorb light. So ethylene, I've written here, it has a lambda max of 174 nanometers. Anybody know offhand what the visible spectrum is?
400 to 700.
400 to 700, very good. Yeah. Do you need to have that memorized? Probably not. Depends what you end up doing. Obviously, if you become a photochemist or if you study vision or something like that, you should probably have it memorized. But 400 to 700 is nice. I like it because if you're going to be seeing chemistry talks, you're going to see wavelengths. And when I say chemistry, you could be in the physics department, you could be in biology, you could be in engineering. Probably less of this in English, but if anybody ever sees an English seminar where they bring in the visible spectrum, let me know. So you're not seeing any of these, all right? All three of these molecules are colorless to you, okay? Ethylene, you guys have seen polyethylene, but in polyethylene the pi bond is gone. We'll talk about polymers at the end of the semester, but polyethylene is made by breaking the pi bond. Ethylene itself is a colorless gas. If you dissolve it in solution, it's colorless. The same is actually true of butadiene. So now we have two conjugated double bonds, and look at that, the lambda max actually moves toward the red. So the longer wavelength light is redder. So we would say that the lambda max shifted toward the red by like, oh crap, I can't do math. Let's like 50 nanometers. So that's quite a bit. And then if you add another double bond, it's like another, 40 nanometers just about for every double bond there. So why is that? Well, if you think about this, right, the pi bond here so in ethylene, carbon-carbon double bond, we've got 2 electrons in a pi bonding orbital. That's our pi bond. And then with that, right, so this is, right, if you look at the 2 p orbitals overlapping, the nodes of a p orbital, like one node is positive and one node is negative. Those are phases. Like this is stuff that's hard to think about in terms, there's not real good physical analogy. We make analogy to waves. Quantum mechanics, quantum physicists make analogies to waves because that's what the math says, right? If you look at the math of an orbital or the math of an electron, it looks like the math of a wave. And that's where we say electrons have wave-like character, right? Electron subatomic particles have both wave and particle properties. Turns out orbitals, which aren't actual things, right? Like an orbital exists whether or not there's an electron to put in it. So you can have a vacant orbital that's there. But it's really just an energy level that could be occupied. Is that a physical thing? Again, philosophy department. But the equations, right, you can put them together so that the plus nodes are together and the minus nodes are together. That gets us what we would say, that's analogous to constructive interference. We get this bigger orbital. Right, so the pi bonding orbital then winds up bigger. There's a node at the atoms, but the space available for the 2 electrons to run around is actually bigger now than the space in just the 2, if they're confined to an atomic orbital. This energy level, the non-bonding line, is, for comparison, the energy of an electron in an atomic orbital. So if you have electrons that have non-bonding character, they're not more stable than they were before, they're not less stable. Those are going to be lone pairs, right? These are typically going to be lone pair electrons, or non-bonding. And the energy difference, there's a little bit of energy gap there. All right, well, you can also put these two orbitals together destructively, where the plus node on top matches up with a minus node, and on bottom a minus with a plus. And that looks like destructive interference. And actually then, what's left of that orbital is very small. Doesn't overlap really, but it's just kind of outside. And this is an anti-bonding orbital. So this is a pi anti-bonding. Right, so if you put electrons into an anti-bonding orbital, the molecule becomes less stable. So we don't typically see, one reason you guys probably haven't discussed anti-bonding electrons a whole lot is the molecules that we actually work with, right? If it exists, we can build a desk out of it or drink it. Probably doesn't have a lot of anti-bonding electrons. All right, so ethylene, if we look at the pi electrons of ethylene, 2 pi bonding electrons, 0 pi anti-bonding electrons. Now, what happens if ethylene absorbs 174 nanometer photon, right? So that lambda max is the wavelength that ethylene absorbs photons the best. 174 nanometers, way in the UV. High energy. So what physically happens to ethylene when it absorbs that photon?
The electron changes the orbital.
Right. So this is conservation of momentum. Conservation of energy, conservation of momentum, conservation of angular momentum. All right. A molecule can't absorb a photon and just do nothing. Some physical change has to happen that exactly equals the energy of that photon. Also can't make change, right? If I'm an ethylene molecule and I absorb 174 nanometer photon, this change happens. One of these jumps up to here. And I would end up with, so I'll draw one down. I'm sort of sorry for that. All right, I would end up with something that looks like that. I would have effectively broken the pi bond. Because now I don't have 2 pi bonding electrons. I have 1 pi bonding electron and 1 pi anti-bonding electron. That is 0 pi bonds, 1 minus 1. All right, if I get hit with a 50 nanometer photon, right? That's enough energy for that change to happen, but the molecule can't make change. So this is, you hear quantum mechanics, things are quantized because they have to happen with exactly the right energy. So this molecule can't really be hit by like 10, 1740 nanometer photons. Right? It takes one 174 nanometer photon to do this. And actually then, because it's a molecule, this is going to shock you. More complex than I've let on. And so you can see sort of a range, but 174 is the most common energy of photon to be absorbed. It tails off. In the spectrum, you'd see a peak at 174, and it would sort of tail a little to the red and tail a little to the blue. But the point I'm trying to drive home. So some of you look like you've seen this, some of you are looking like you'd like to be somewhere else. You don't have to know quantum mechanics for this course. We're not going to solve any differential equations, because it would take me most of the semester to figure out how to do that. But you need to know this, that there's conservation of energy. So if you start with a system at energy x, whatever happens, energy x has to come out the other end. So if a molecule gets hit by a photon, right, E equals, for the photon, E equals h nu, which is the frequency, or hc divided by the wavelength. So that 174 nanometer photon, you're not going to have to calculate that. I'm not going to make you do that. 174 nanometer photon has a certain amount of energy, right? And that energy matches this energy gap. Basically what we're saying is, in ethylene, the antibonding orbital exists 174 nanometers worth of energy higher than the bonding orbital. So what does that mean for butadiene? How much is the orbital that gets transferred to above the orbital that gets transferred from? You can put it in nanometers. 217, right? So why do these two orbitals closer together? And the answer is, how many pi bonds do we have here? How many pi antibonds do we have? Nope. 2. There are always as many antibonding orbitals as there are bonding orbitals. And they get squeezed. So, right, this antibonding orbital, if we had one double bond, this antibonding orbital, there's one higher and one lower. And for this bonding orbital, one higher and one lower. How many pi electrons do we have? About 4. So fill those in. Nope. Crap. Sorry. Jeez. All right, I'm going to have to burn this tape. The spins, those arrows are electron spin. This is only what I did my PhD on. Those are electron spins. Spin is a whole other thing that we're not going to get into in this class. I'm sorry, because I can talk about it for decades now. Spin, again, it comes from the math. You probably know that an electron has a spin of plus and minus a half, up and down. They can be paired. And so in most molecules, all the spins are paired. Paired just means that if I know the spin of one of them, I know the spin of the other. Spins can also be unpaired. Like here, I've shown them paired, one up, one down. You could also have an excited state ethylene. So the excited state is after absorption of the photon, that energy that's in it. You could also have an excited state ethylene where the spins are unpaired. Right? That's actually a little more stable, but again, don't worry about that. So for butadiene, come way back down here. Sorry, folks at home. Did I draw? I know, I never drew this. Crap. I start panicking in the last 10 minutes of class. Draw the molecular orbital of butadiene. I'll save my panic by making you do so. Okay, so butadiene's got 4 carbons, 4 p orbitals. So if we mix 4 p orbitals, we have to get 4 pi orbitals. And again, this can be plus. You can put them all in phase, right? All the p orbitals lined up in phase. How many bonds do we get there? How many pi bonds do we get there? In the orbital I've just drawn, this one right here. How many pi bonds are there? Got some votes for 2. Because you look at the molecule, what do you think? We got 3. And here's the problem, like, this is I don't do this on exams, but like you look at that, like butadiene has 2 pi bonds. Dr. Jones, what the hell are you asking me? Like how many pi bonds? You drew 2. A pi bond are 2 overlapping p orbitals separated by a sigma bond. So right? There's a pi bond just like you expected, and there's a pi bond just like you expected, and look, oh, what is that? P orbital in phase separated by a single bond. There are 3 pi bonds in the most stable molecular orbital for butadiene. That, and I'm going to draw this like we're drawing on top. right? All 4 of those p orbitals are in phase. That's the most stable molecular orbital. It's got a bond order of 3. Right? The bond order, which you may remember from Gen Chem, it's just the number of bonding interactions minus the number of anti-bonding interactions. Right? Here there are no non-anti-bonding interactions. Each carbon in the molecule is pi bonded to the one next to it. 3 pi bonds. And so I've drawn that as 3 open circles. I'll show that again here in a second. So let's do the next one up. You can imagine I can't control my marker. So let's have a pi bond. This is maybe how you imagined it in the first place. Right? So the 2, a pi bond on the end and a pi bond on the end, just like it's drawn in the structure. Pi bond, sigma bond, pi bond. But now, if you look at the bond order, complicated organic chemistry math there. Right? There's a bonding interaction here, there's a bonding interaction there. 2 bonding interactions. That's an anti-bonding interaction. Plus node with a minus node. So this is still net, this is a bond. This is a bonding orbital. And that goes right, so that's a net bonding orbital, but it's higher in energy. The bond order is 1, not 3. So it's less stable. Higher in energy. And then you can go on, you can do more of this. I'm not going to belabor it. You can draw it some. We'll work on this a little bit more next time. If you're worried, I'm not going to ask you to do a ton of this in class, but that next one up then has 2 antibonding orbitals or interactions and 1 bonding. Right? Antibond, bond, antibond. So this is a bond order of -1. That's antibonding, and butadiene doesn't have electrons in that. Finally, if they all alternate, the bond order here is -3. This is the least stable. That's the highest energy, and so that's not, right? There's no electrons there. Now, when butadiene absorbs a photon, remember, energy of the photon equals h nu. So I will abbreviate photons as h nu, Planck's constant times frequency. What happens is one of the high energy electrons jumps up to the next lowest orbital. Make sense? And because of these things are getting squeezed, like as you fill these in, we actually have some antibonding character to this orbital. It's a little higher in energy than just a single pi bond. And there's a little bit of bonding interaction in this lowest unoccupied orbital, so it's a little bit lower than a regular pi antibonding orbital. Okay, so the orbitals get squeezed together as we have more and more conjugated alkenes, as we put more and more pi bonds on there, that gap becomes lower and lower. And in fact, this gap governs so much chemistry. So there's 2 abbreviations you ought to know out of this, and then I'm going to stop class. You guys should read about aromaticity in chapter 17 for next time. This orbital is the highest energy molecular orbital that's occupied. So this is the highest occupied molecular orbital. We're not done yet. Okay, what's the next one? LUMO, lowest unoccupied. So lowest unoccupied molecular orbital. In chemistry, a good chance MO means molecular orbital. Less likely is that it means molybdenum. If they're both capital, it's a molecular orbital. So highest occupied versus lowest unoccupied. And seriously, pretty much every ionic reaction you guys have ever seen is a homo-LUMO interaction. It's the homo of the nucleophile, the thing with electrons, right? The higher in energy those electrons are, the faster it's going to react. And if I'm a nucleophile, where am I putting my electrons? I'm putting them in the lowest unoccupied orbital I can find, putting them in a LUMO. So the HOMO of a nucleophile reacts with the LUMO of an electrophile. With light, and it's just one reaction, the HOMO, the most likely thing for the lowest energy thing to happen would be a HOMO electron to move to the LUMO orbital. All right, read over benzene and aromaticity, and that's what we're going to talk about next time. So that was 30 minutes of class. You guys are wondering, what's he going to ask on this? Like, how many differential equations am I going to have to solve? The answer is 0, plus or minus 12. I might ask you to draw an MO, or at least explain things in MO terms. Maybe predict which molecule absorbs light at the longest wavelength. We'll see some problems on that. We'll talk about it more in class. If quantum isn't your thing and you haven't seen any of that before, you're okay. Don't panic. I'll see you on Wednesday. Come for a ride, folks at home. Say hi to everybody.